Okay, so let's look at this problem. The base of the triangle is given 12, and the paper is folded down over the base. Okay, so this is our base 12, and we are folding this AB. C. Okay, okay, we are gonna. This paper is gonna be folded down over the base with the crease the parallel to base of the paper. Okay, so we are told that this is our this DE that we are actually using to fold it. So this triangle CDE is actually folding on like kind of symmetry, not actually kind of symmetry, it's just symmetry. We are just taking this DE as line of symmetry and then taking this triangle and making the reflection. Okay. So the area of the triangle that projects below the base is 16%. Okay, so which means this region right here. Okay, so this region right here is 16% of the area of the ABC. What's the area of the Okay, so with this one, I think we are going to use the parallel lines because that's given for us. And also, we should probably use the area that is 16%. So those are the two information that we really need to use it for sure. Just because we are given parallel lines, I'm gonna just assume we're gonna have a lot of smaller triangles. So even though we don't really know it yet, but we may probably find it. So that's why I'm gonna just go ahead and find some of the angles, and then I'll just see if we have any parallel like smaller triangles. Since when you take CDE, okay, this triangle, and fold it along this DE, and you are gonna get this triangle. So I can call this guy to be C prime, and when you take this one and take the reflection through this DE, this point C has to coincide with this point. So for that reason, I'm gonna say this angle and this angle has to be equal, because when you take this triangle and take the symmetry of that triangle along this line segment DE, this angle will be corresponds to this one, and similarly this angle right here should correspond to this one. So that is nice because we have at least some sort of equal angles. And I do already know that's given in the problem. These two lines are parallel. DE and AB are parallel because we are told that crease D is parallel to base of the triangle. Base is AB and crease D will be right here. So they are parallel. And if DE and AB is parallel, the angle right here and angle right here has to be same because those two angles are alternate interior angles, and that makes these two angles congruent. And similarly, this angle and this angle are also alternate interior angles, just because of the DE and AB are parallel. And now I do have this angle, and right here, this angle needs to be equal to each other since they are vertical angles. So this C prime E and AB are two lines intersecting at this point. The opposite angles are vertical angles. They are congruent. And the same idea with this part. So this guy right here has to be same as D, whatever this angle and A. So I can tell this like DTA, if I call this is T, whatever. Okay, so now we're almost there, I think, because we have a lot of same angles. So let's maybe change a few more angles just to see if we are gonna get some smaller triangles. So since we already know DE and AB are parallel, so just quick reminder, when you have two parallel lines, let's say these are the two parallel lines, when you have the third line passing through those two parallel lines, then we already know there are a lot of congruent angles. And then this guy and this guy are called corresponding angles when this guy and this guy are parallel and this angle is equal to this angle. If you look at this part right here, so this angle and the angle A has to be equal to each other as well, because DE and AB are parallel, so which makes this angle same as this one, this angle same as this one. I think this is going to be really helpful because we did get something right here that is isosceles triangle. So we should probably use that information. So I'm going to call this guy and this guy are equal to each other. And same reason, this guy and this guy will be equal to each other as well. And I already know this guy is parallel to this one, and this D, C prime E, and these CE are congruent triangles. So that means the angle C right here and angle C prime right here has to be congruent. And without really saying that, we can already see that this angle same as angle A, this angle same as angle B. So this small triangle right here and ABC is similar because they already have two pairs of angles that are congruent to each other, and angle C and angle C prime is also same, so they have three same angles. So which is really nice. So I can conclude that, okay, I'm gonna call this guy maybe X, maybe Y. So the C prime, X, and Y is similar to, so this is a triangle, is similar to, since I start with C prime, corresponding angle is C, so triangle A, X is this angle right here, the same angle is A, so I will go with CAB. So the C prime XY is similar to CAB, but I do need to use this information. So I need to use that information, which is 16% area. But before we do this, I just want to remind something about the similarity and the area of the similar triangles. So when we have two similar figures, or any triangles or any different figures, the ratios of the similarity is equal to square root of the ratios of the areas, or I could say the square of the ratios of the similarity is equal to ratios of the areas. So it's kind of a little bit challenging to say. So let me just write actually ratios. So if I want to start with the smaller triangle, so XY, okay, XY, this is the side plan, divided by this side is opposite angle C. Angle C is right here in the larger triangle that is opposite to AB. So the ratio of this XY over AB is equal to, if I want to take this one, maybe C prime Y, which is opposite this angle, the same angle right here that is opposite to BC. And if I want to use the last one, so that should be X C prime or C prime that. And this is going to be opposite to AC. So when you take the ratio of the similarity like this one, then we could square this ratio to find the ratios of the areas. So which is I'm going to actually do that. So if I square this one, or this one, or this one, this has to be equal to ratios of the areas. So I'm going to use this notation to show the areas. So the area of the XYC actually prime, and this has to be divided by ABC. Okay, so that should be ratios of the ABC. So again, when you know the ratios of the similarity, you could square that number to get the ratios of the areas. So if you are not familiar with this idea, so I highly suggest you to look at the similar triangles and the relation between similar triangles and their areas. But this is basically the result. So if you are not convinced why this is the case, then you might want to look at the maybe more explanation on this. Okay, but I'm going to use this idea. So we are told the area is 16%, this region. So if you look at this one, I'm going to write at least XY. Okay, XY over AB. I can take just one ratio. The square of this one has to be 16%. Like if this is the 16%, then ABC will be 100%. So I can say 16 over 100 is going to be ratio of the XY over AB to the second power. And this is basically, I can take the maybe square root after simplifying. So if I take the square root, then xy over AB has to be 2 over 5. Okay, so we got something. This is really important for us to know it at least at this point. So this is 2x. Like I'm gonna say this is 2 over 5. Maybe I could say, like, I'm gonna use 4x over 10x instead of 2 to 5. You are gonna see why I actually use this one. I just don't want to deal with the fraction stuff. That's why instead of 2x to 5x, I just made it like 4x to 10x. Since actually I have x and y, maybe I could say this is a or something. So let's do that way. 4a over 10a. So let's say this is 4a and xy is 4a, and ab will be 10a, right? So, but it doesn't help too much, to be honest. But if I put this triangle back into this CDE, then I will get a line that is going to be same as xy. So I'm going to do it that way because I just want to find the ratio of DE to AB, and then I don't know that yet. So that's why I'm going to actually draw a line, something like this way. Okay, so let's say this is my line segment. Okay, so this is basically xy. When you put like take this C prime and put it back here, so this triangle will be this triangle. So which means the xy right here is 4a, so this guy has to be 4a as well. Okay, so this is 4a and AB is 10a. At the same time, I do know since I just put it back to this original like spot, then this guy right here, if I call maybe this is y prime and this is maybe x prime, this distance y prime e and y and e has to be same because those are symmetric, and the same idea, this guy and this guy has to be equal to each other. So then I already know ratio xy, okay, x prime y prime over AB. This is same as this one, so that's already 4 over 10. Again, this is coming from 2/5. I just used 4 over 10. So if that is 4 over 10, I do know just because of the similar triangles. So this one divided by this one should be 4 over 10 as well, because cx prime y prime is similar to a CAB, because this is parallel to that one. So you have this angle same as this one, this angle same as this one. So cx prime y prime is similar to CAB. So then ratio of this segment to AB, which is 4 to 10, has to be equal to CX prime over CA. So based on that, if you have 4 to, let me write this, CX prime over CA. So if this is something like multiple of 4, maybe I can tell this is 4B, then the CA has to be 10B. And I do know this piece and this piece are equal to each other, so that should be 3B, and that should be 3B as well. So we are almost there. So we are looking for DE. So if you take a look at this triangle, okay, CDE and CAB, they are parallel. So the ratio of the CD over CA has to be DE over AB. Okay, so CD is 7B, CA is 10B, so I can just say 7/10, and DE is what we are looking over AB, which is given 12. So if you do a cross multiplication, you got 84 over 10. So DE has to be 8.4. And this is it.